Hello, and welcome to ECE-340, Engineering Probability, Random Variables, and Random Processes. I'm Dr. Bradley Duncan, and I'll be your instructor this semester. This is going to be the first of a long sequence of videotape lectures that I'm going to make available to you online. Today we're going to talk about three primary topics. One is to introduce some of the notation that I'm going to use for the rest of the semester. Second, I'm going to introduce the various approaches to probability that we might encounter, compare and contrast them just a little bit. And I'm going to spend some focus time on the relative frequency approach to probability. We will see the relative frequency approach several occasions throughout the semester. So I think it's fair to ask at this point, what's the purpose of a course in probability? Well, probability ultimately centers on the study of chance or random experiments. And these random experiments may or may not actually be performed. They might be the product of a thought exercise on your part, or they might be something that we actually go into the laboratory and perform. Our goal is to use mathematical tools and techniques to quantify the likelihood of various outcomes or collections of outcomes, and to do this in such a way as the randomness of the experiment somehow makes sense and is described in such a way that useful information can be extracted and or reliable predictions about the future can be made. That's where we're going, and that's what we're doing. So to begin, let's talk a little bit about the notation that we're going to use. And again, this is my notation. It's notation that's that I've adopted over the years. Different instructors, various textbook authors might use something a little bit different. Notation. The first bit of notation is a capital English letter with an arrow written over top of it. This serves to represent what we will know as a chance experiment. Early on, our chance experiments are going to be represented in words. Later on, they might be mathematically described. Next bit of notation is a capital S. Capital S will stand for the sample space. The sample space will be the collection of all possible outcomes to our chance experiment. An outcome, then, will be represented by a lowercase English letter. An outcome is the result of performing a chance experiment. It's what occurs. It's one of the possible things that can occur when I perform a chance experiment. An outcome is also known as an elementary event. I will almost always call it an outcome. Next bit of notation is a capital English letter subscripted with a number. This will be an event. An event is a collection of outcomes. The sample space, being the collection of all possible outcomes, is an event. It's a special case event. In general, events can have a single outcome. They might have no outcomes. They can include all outcomes, meaning the sample space, or more interestingly, it's a collection of the possible set of outcomes. Speaking of nothing occurring, we'll use the lowercase Greek letter phi to represent the null set, or null event. And this is the event that nothing occurs when I perform a chance experiment. So let's talk about the sample space and the null set just a bit more. The sample space is also known as the certain event, aka also known as the certain event. By that I mean that it is 100% likely, it's absolutely certain, that something will happen when I perform a chance experiment. Moreover, an event is said to have occurred if any outcome in that event has occurred. So, an event that has multiple outcomes in it is said to have occurred if we perform the chance experiment and at least one of the outcomes in that event occurs. So if we think of the sample space as all possible outcomes of a chance experiment, when we perform a chance experiment, something is going to occur. One of the possible outcomes is going to occur with 100% regularity, and so the sample space is known as the certain event. By contrast, the null set is known as the impossible event, meaning that it contains no possible outcomes. So if we perform a chance experiment, we know that something will occur, meaning that it is absolutely impossible or 0% likely for nothing to occur. The null set is therefore known as the impossible event. It's not possible for nothing to occur. All right, so to introduce this notation a little bit more concretely, I want to do what I think is a trivial example. My example is going to be this. My chance experiment is going to be toss two fair coins and observe or record heads and tails. All right, and by fair in this example, I mean that it's equally likely for my coin to show up heads or tails. Another thing, I'm tacitly assuming that the two coins in this experiment are somehow distinguishable from one another. One's a nickel and one's a dime, or one's green and one's blue, but somehow I'm able to distinguish between these two coins. All right, so We toss 2 fair coins and we observe heads and tails. It should be clear to you that there are 4 possible outcomes. We might list them like this. A1 is tails, tails. A2 might be tails, heads. A3 might be heads, tails, and A4 will be heads, heads. So there are 4 possible outcomes. Four possible outcomes. So the sample space, which is the collection of all possible outcomes, would look like this. A1, A2, A3, A4. All right? So from here we could then define perhaps some events. Let's look at some events. A1, capital A1, might be the collection of outcomes A1, A2, and A3. This is the event that there is at least one tail up. One tail up, one tail showing. We might have another event, A2, which might include events A1 and A4. This is the event that both coins show the same side. We might have an event, A3, that's just a single event. 2 heads up. I'm sorry, yeah, 2 heads up. Outcome A4 is 2 heads up. And we might have a 4th event that's nothing. That's the way we would represent the empty space. I toss 2 coins, and they both vanish into thin air, and nothing results. Of course, we know that's absolutely impossible. All right. For those of you who are somewhat familiar with Venn diagramming, my events and outcomes from this previous experiment, or from this previous example, might look something like this. For those of you who are not familiar with Venn diagramming, that's okay. In about 2 videos from now, we'll spend quite a bit of time talking about Venn diagrams. But for our example that we just did, Venn diagram would look something like this. This will be our sample space S. And inside of the sample space, I'm going to have a collection of outcomes, A1, A2, A3, and A4. My event A1, which included outcomes little a1, little a2, and little a3, looks something like that. That was event capital A1. Event A3 was just outcome little a4. And down here, an event which encompasses no possible outcomes was my empty set, event A4. All right, that's just a very simple Venn diagram analysis of our toss 2 dice and observe head tails chance experiment. All right. Before moving on, I want to make one other comment, that outcomes can be continuous or discrete. And they can also be finite or infinite. All right, outcomes can be continuous or discrete, or they can be finite or infinite. The or the example that we just did when we tossed 2 dice and observed heads and tails, that was clearly a discrete, finite set of outcomes. It was either heads, tails, heads, heads, etc., and there were only 4 possible outcomes. So our previous example was discrete and finite. We'll have occasion to look at many continuous, in some cases infinite, collection of outcomes for various chance experiments as the semester unfolds. All right. Next, let us talk a little bit about the approaches to probability. There are 4. The most common approach to probability is what we might call subjective probability. Subjective probability. It's the most common. At the very best, it is a wise, educated guess. Something like looking out the window and saying, looks like it's going to rain this afternoon. That might be a wise guess informed by your knowledge of what storm clouds look like, but it in fact is not very precise. In fact, it's the worst approach for precision analysis. The second approach that we might encounter is the approach which makes the assumption of equally likely outcomes. I'm not going to spend a lot of time talking about the assumption of equally likely outcomes. It is actually a special case of the third approach, the relative frequency approach. Let me just write that down. It's a special case. It's a special case of the relative frequency approach, and inasmuch as the outcomes are indeed equally likely, the assumption of equally likely outcomes might be a good, rigorous, valid, precise approach to describing probability. So I'll just say that it's not necessarily a bad approach, assuming that the outcomes are equally likely. All right. The third approach is the relative frequency approach to probability, and I'm going to spend some more time with that in just a few minutes. The third approach is the relative frequency approach. And the relative frequency approach to probability is something we're going to employ quite a bit through the semester, especially when we get to histogram analysis and probability density function estimation. It's actually very good in certain applications where approximation is allowed or must be used. So it's very good. Strictly speaking, for full precision and full certainty of our predictions, we're going to need infinite sets of data. But as long as we have large sets of data, the predictions that we can make from the relative frequency approach are really quite good. And I will say this, that the relative frequency approach to probability is best if we're dealing with finite and discrete chance experiments, meaning that we have a finite collection of outcomes and they are discrete and easily distinguished from one another. And the fourth approach to probability, and the approach that we will spend the overwhelming majority of our time using this semester, is known as the axiomatic approach. The axiomatic approach. All right, the axiomatic approach uses mathematical tools in the most rigorous way. So it's the most mathematically rigorous. It's the most mathematically rigorous. It uses set theory and other mathematical tools that you are already familiar with. The axiomatic approach starts by defining the properties that probability must obey. That's where it starts. And those properties are said to be axiomatic. The good news is there are only 3 axioms. It always amazes me that there are only 3 axioms of probability that we can use to build an entire body of axiomatic probability theory. All right. Let's now spend some time talking about the relative frequency approach to probability and do maybe a little example. Actually, what I'm going to do is I'm going to more or less leverage the example we did earlier, flipping two coins and observing heads and tails. We had 4 possible outcomes, clearly finite, clearly discrete. So imagine that we have our experiment that has 4 possible outcomes. And those outcomes are going to be A1, A2, A3, and A4. We're going to perform our experiment n times. I'm going to perform my experiment capital N times. In each one of the outcomes occurs an n sub I number of times. So outcome A sub 1 occurs capital N sub 1 times. Outcome A sub 2 occurs capital N sub 2 times, etc., etc., etc. In other words, the total number of times we perform my chance experiment equals N1 plus N2 plus N3 plus N4. And you can see how this would be extended if I had any variety number of discrete possible outcomes. The relative frequency for a given outcome is represented this way. All right. The relative frequency, little r, of outcome, little a sub I, is the ratio of the number of times outcome a sub I occurs, that's capital N sub I, divided by the total number of times we perform my chance experiment. Another way to write that is that, or rather an observation, is that 1 equals n sub 1 divided by n plus n sub 2 divided by n plus n sub 3 divided by n plus n sub 4 divided by n. All right? Another way of writing that last expression is that relative frequency A sub 1 plus relative frequency of A2 plus relative frequency of A3 plus relative frequency of A4 equals 1. Generalizing this a little bit, we could write that summation from I equals 1 to capital M of R A sub I equals 1, where M, in this particular thought experiment, we're assuming we have 4 possible outcomes, but in general I might have M possible outcomes. All right. Now, if we perform our chance experiment an increasingly large number of times, meaning that if n approaches infinity, n is the number of times we perform our chance experiment. If n approaches infinity, we perform our chance experiment an increasingly large amount of times, then if n approaches infinity, then my relative frequency of outcome A sub I, if also we assume that my chance experiment is statistically regular, if my chance experiment is statistically regular, then as n approaches infinity, my limit will approach the true probability my relative frequency will approach the true probability of outcome A sub I. This is the relative frequency on the right-hand side. So if I perform my chance experiment an increasingly large number of times, if my chance experiment is statistically regular, then this limit, the limit of my relative frequency as n approaches infinity, will approach a fixed number, and that fixed number is the true probability of chance experiment, of outcome A sub I. All right, statistically regular. Statistically regular means that that limit actually yields a fixed number. Means that that limit actually exists. And not surprisingly, we can make this observation, that if I add up all of the true probabilities of the various outcomes, if I have an experiment that has only 4 possible outcomes, then if I find the individual probabilities of each of those outcomes, they have to add up to 100%, because it is 100% likely that something occurs. It's 100% likely that one of those 4 outcomes will occur. And it is true also that 1 equals the relative frequency of A1 plus relative frequency of A2 plus the relative frequency of A3 plus the relative frequency of A4. But in general, these two statements are always true. The relative frequencies must always add up to 1, and the probabilities must always add up to 1. But in general, the relative frequency of A sub I is only approximately equal to the probability of A sub I. And this approximation gets better as the number of times we perform my chance experiment gets bigger and bigger and bigger. Okay? All right. So from this discussion, let's make a couple of additional observations. One, we can more or less verify that the probability of the empty set equals exactly 0. The reason being that exactly nothing occurs 0 times out of n trials. And this is true independent of the size of n. All right? Nothing occurs, meaning no outcome occurs, exactly 0 times out of n trials. And this is true independent of the size of n. It's true independent of the number of times we actually perform this experiment. So we can therefore say that the relative frequency of nothing occurring, which is always 0, equals the probability of nothing occurring equaling 0. Second thing we can observe is that the sample space, probability of the sample space, equals the probability of the sample space is always equal to 100%. If I add up the relative frequencies of all of the possible outcomes, I'm always going to get 100%. It's 100% likely that something is going to happen. And if I take the limit as n, capital N, approaches infinity, my relative frequencies will approach my exact probabilities of the various outcomes, add those up, and it's going to be 100% likely that something occurs. So from all of this, we can then determine that probability always falls between 0 and 1. In fact, the probability of an outcome, the probability of all events, will be a real number that lies between 0 and 1. Probability of events and outcomes is always a real number between 0 and unity in all cases. All right? So, that's all for today. We will pick up next time with a short video introduction to conditional probability. If you have any questions, please do feel free to contact me and let me know. Thank you.